Lewis structures are the way that we represent a covalent bond and a covalent compound called a molecule on paper. Below you see one of examples of a Lewis structure. This one happens to be for the formula PF5, phosphorus pentafluoride. We're going to learn how to set up these things up. It's a very systematic procedure, and there's very many rules that need to be followed. You do need to record these rules and have them available to you while we're in class and we're working. So here are the rules. First of all, hydrogen is always a terminal atom, meaning that it's always on the side. Outside of that, the atom that you have in your compound that is the furthest left on the periodic table is considered to be the central atom. This also has the lowest electronegativity, or the least ability to attract an electron. From there, you're going to take the total number of electrons for bonding. This is the total of the valence electrons of all the atoms combined together and add together. Then to determine the number of pairs, you're going to divide by 2. In order to establish an initial bond, you will place one pair of those electrons between the central atom and each of the terminal atoms. And while you're doing this, you're going to subtract the remaining pairs from the original number of bonding pairs, leaving your lone pairs and your double triple bonds for later. You'll then place pairs around the outside of the terminal atoms to satisfy the octet rule, with the final pairs that are left over going on the central atom. The last rule is kind of a starred rule. It's an if necessary rule. If the central atom does not have 4 complete pairs, you will pull in non-bonded terminal atom pairs to make double and triple bonds so that all atoms have satisfied their octet rule. I know it's a lot to take down. At this point, you should probably pause it and get this recorded, because this is a very, very important information for you in the completion of these Lewis dot structures, which we'll be working on throughout this week. So here we have an example, and the example that I've given you also provides us with the rules over here in the corner, so we can work on that as we go. Alright, so in the compound CCl4, the atom that is furthest to the left on the periodic table is carbon. So we're going to place carbon in the center. Now, because that's the central atom, we'll then place our terminal atoms around it. The next thing that we need to do is collect the total number of valence electrons to figure out how many electron pairs we have to find a home for. So carbon has 4 valence electrons. Each of the chlorines has 7. But we have a total of 4 chlorine atoms. When we add all of this up, we get 28 plus 4 is 32 pairs. 32 pairs of electrons divided by 2 gives us 16 total pairs. 32 total valence electrons divided by 2 gives us our 16 pairs. The next part that we need to look at is we need to place one bonding pair between the central atom and each of the terminal atoms to establish an initial bond between them. If we take our 16 and we then subtract the number that we used, we are now down to 12 pairs. Now we're going to place our pairs around the outside of the terminal atoms to satisfy their octet. So count with me. 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair, 7, 8, and 9, 10, 11, and 12. Subtract that from our total, we have 0 pairs. Now we need to check every single atom. Remember that there is an overlap of the atoms so that pairs are shared. So let's look first at this terminal atom on the left side. If we place a box around it, you can see that we have 1, 2, 3, 4 pairs. And those 4 pairs equal 8 total electrons, or your stable octet. We can do this for each of the chlorine atoms and find that each of the chlorine atoms has a satisfied octet. The last thing we need to check is our central atom. Our carbon is sharing with each of the 4 chlorines to get 1, 2, 3, 4 pairs. Therefore, the Lewis dot structure of CCl4 is good to go. I know there's a lot going on with this slide, but we're going to practice this in quite a bit of depth in class. The last thing to consider when we're talking about Lewis structures and covalent bonds in general is bond strength. The strongest of the bonds is a triple bond, and that's over here. The weakest of the bonds is a single bond. Because remember, think about bond strength as the number of hands holding two people together. I know we don't have 3 arms to hold us all together, but if we did, there would be a greater connection between us and the people next to us than, say, a single bond with 1 arm extended. In the middle of the two is a double bond. In order to break apart any bond, a certain amount of energy is required. Their term for that is the bond dissociation energy. What type of bond would have the greatest bond dissociation energy? Hopefully, you came up with the answer of a triple bond. Okay, so looking at these two Lewis structures, which one has the greatest strength, the highest energy, the most energy required to break it apart? Over here, on the left side, we have HCl. What type of bond does HCl have? Yes, we know it's covalent, but what kind of covalent bond is it? Focus on the area between the hydrogen and the chlorine. See that there is one pair. This is a single bond. Over here on the right, what do we have going on in between? We have 3 lines. 3 lines represents a triple bond. According to the information we just learned on the previous page, the greatest strength, or the one that would require the greatest energy to break apart, would be this one over here. It's a quick summary of Lewis dot structures. We'll be working with these through several activities in class.